These are some of the most common types of rechargeable batteries. They vary in size, capacity, and charging voltage. However, they all have one thing in common. They require a battery management system, BMS, to operate safely. A BMS continuously monitors and manages critical battery parameters, including the voltage of each cell, the charging current, the discharging current, and the battery temperature. If any abnormal condition is detected, the BMS immediately disconnects the battery from the external circuit to protect both the battery pack and the connected equipment. To address this issue, I designed a BMS that uses through-hole MOSFETs together with an aluminum heatsink. This design eliminates the main weaknesses found in many BMSs currently available on the market. Although using through-hole MOSFETs and an aluminum heatsink increases the overall thickness of the PCB, this is not a significant drawback, considering the improved durability and current handling capability. This is an open source project, and I have shared all the design files in the pinned comment below this video. This video is sponsored by JLCPCB, one of the world's leading PCB manufacturers. Their PCBs are of excellent quality, and their production turnaround is extremely fast. If you've never used their service before, here's a quick guide. I'll show you the easiest way to order PCBs from JLCPCB. First, create an account. You can sign up quickly using the link provided below this video. Next, upload the Gerber file that I provided. Once the upload is complete, you can perform a final inspection using the built-in 3D viewer. This tool is extremely useful, allowing you to easily identify design issues and preview exactly how your PCB will look after fabrication. After that, you can choose the PCB color, board material, and configure many other manufacturing options to suit your needs. Once everything is ready, simply add your order to the cart and proceed to checkout. Don't forget to apply the available coupon codes to help reduce the cost of your PCB order. This is the PCB I received after about 2 weeks of waiting. As always, the PCB quality is excellent, with flawless manufacturing and a professional finish. If you need your boards more quickly, you can choose DHL Express shipping. It offers much faster delivery, although the shipping cost is significantly higher. The control IC and the supporting components are all surface mount SMD devices, so they need to be soldered first. This is a rather tedious process. Once this prototype is complete, I'll use JLCPCB's PCBA service to save time on assembly. Hand soldering SMD components is also not ideal because the fumes generated by the solder flux can be harmful to your health. These 4 1/4 watt resistors are part of the passive balancing circuit. When a cell voltage exceeds the balancing threshold, the excess energy is dissipated through these resistors. To be honest, however, they are not particularly effective because the balancing current is simply too small. The heart of this BMS is a dedicated battery management IC, the BM3451, manufactured by BYD. As one of the world's leading manufacturers of rechargeable batteries in electric vehicles, BYD has extensive expertise in battery technology. That gives us every reason to have confidence in the reliability and performance of this battery management IC. To enable overcharge and over-discharge protection, the BMS needs to measure the battery current using a shunt resistor. Many low-cost manufacturers use the PCB copper trace itself as the shunt resistor. However, this approach is not as accurate as using a dedicated precision shunt resistor. Next, we'll mount the MOSFETs onto the PCB. I'm using NCEP85T14 MOSFETs, each rated for 85 volts and a maximum continuous drain current of 140 A. All of the MOSFETs used in this project are brand new. This BMS is designed to handle a continuous current of 100 A's. With multiple MOSFETs sharing the load, each device carries only a little over 10 A's, which is just a small fraction of its rated current. As a result, the MOSFETs operate well within their safe operating range, providing excellent reliability even under sudden high current loads, such as motor startup. Here is the completed board. Installing the BMS is very straightforward. Simply connect B0 to the battery negative, GND, then connect B1, B2, B3, and B4 to the positive terminals of each cell in the series string. The BMS switches the battery's negative terminal, while the positive terminal is connected directly to the external load. This 45 Ah battery pack supports a maximum charging rate of 1C. I'll set the charging current to 40S and test whether the MOSFETs operate properly. So far, all BMS parameters are normal, and the MOSFETs remain cool.